Hi, and welcome to Geeks for Geeks. Today, we would be discussing yesterday's problem of the day, that is special digits. So, hi everyone, I'm Siddharth Hazra. I'm an SD at Geeks for Geeks. Apart from that, I'm also a candidate master on code forces. So, without any further ado, let's get started. Hi, Madhba Joshi. Okay, so let me just share the screen itself. Hi, Rishit. Okay, seems good. Okay, so let's talk about the problem first. Talking about the first feedback of this problem. This problem is an easy problem, but on the medium side. Okay. And if you already know something known as binary exponentiation, then if you already know modular inverse, or you can say that you already know the Fermat's little theorem too, and then you're already familiar with Fermat's little theorem. Okay, and then you're also familiar with NCR. If you already know the all this thing, then only this problem is an easy problem for you. But to be honest, this problem is a very good problem if you don't know this. Why? Because in the aspect of solving this problem, you would go out and you would learn about binary exponentiation, modular inverse, and Fermat's little theorem. So today my explanation would be that I would give you a brief of all of this. And if you are still not able to understand, kindly go and read all of that in depth. Come back and solve up this problem after seeing the video. So now let's start with what is given and how can we say that we require all of this. Okay, now we are told that we are given five integers. The first one is a, b, c, d, and n. Okay, then it is told that all the integers of length n means that the number of digits is n. So I would say the number of digits is n itself. This is first condition, and it should contain only a or b. So a is from 0 till 9, b is also from 0 till 9. How can I say that? I can say from this 1 till 9. Sorry, it is 1 till 9. So it should only consist of a or b only. Please remember this. That is why I'm writing this in dark. Okay, so all the numbers which are n digit and it consists of only a and b. Let's say a is 1 and b is 2 and length is 2. So what I can do is I can have 2 1. Okay, I can have 1 1, then 2 1, just the reverse of it. Then I can have 2 2 itself. Okay, this is how I can have all these numbers. Okay, these are all the numbers that I can frame with using only a and b, and the length is 2. Now let us move forward, and we are told that these all are good integers. All are good integers. Now among the good integers, all those integers whose sum of digits. So let us first find the sum of digits. Sum of digit here is 2, the sum of digit here is 3, sum of digit here is 3, sum of digit here is 4. Okay. Contain either C or D, that is 3 or 5. So 3 or 5. Do we have any 5? We should have. So sum of the digits is either 3 or 5 or both in it. Sum which contains 3 or 5, and this is, so 3 or 5 is only 2. That is why the number of values which are best integers, the value is 2. So first you need to find all the integers with length n. Then you need to move forward, and it should consist of only a, only b, or a or b. Okay. Then from them you need to find the best integer. What is best integer? After having the sum of the digit, it should consist of either c or d. Okay, that is why this is the output. Let us take one more. Do we have a simple one? No, the values would be many more. No, it would be very large. Okay, so can't be shown. Okay, this, no. Okay, so basically this is what you need to do. So now the very first approach you can think of is that I would n digits. So if I am given that I want all the numbers with 2 digit, that would range from 1 1. Why 1 1, not 1 0? Because it is told that each of the digit would be from 1 to n, not 0 to 1. So 1 1 till the value 99. We have all the numbers which are of 2 digit. Then we would iterate from 1 1 to 99, and then we would say all the numbers which would give me the answer, like they would contain c or d in their sum. They are the best integers. I would count them and I would return them. Simple enough. But see, the problem is, and the time complexity of this approach would be linear, because we are just checking and iterating. So it entire, like for in to take out the sum of a particular integer, it is just the number of integer, that is, I can say it is constant or log n, whatever be the scenario. So okay, so now as you can see, it is still 10 to the power 5 and it is 9. So it would be very large. Okay, it would be absolutely very huge. And as you can see, even without telling you anything, it is told as the best integers can be huge, print it modulo 10 to the power 9 plus 7. So it is already telling me, like this question is only giving me a hint that the number of values is definitely greater than 10 to the power 9 plus 7. But in 1 second, we can perform only 10 to the power 8 operation. So to perform 10 to the power 9 operation, even if we process all the best values in constant time, then also this is greater than this. So we would definitely get a TLE even before implementing it. So we need to think of something better. Okay. So now the very first idea is, it is not asking me for the numbers, but is just asking me the count of the numbers. Okay. This is the very first hint. Okay. Numbers are not needed, but the count of the numbers are needed. Count of the numbers are needed. Number is not needed, only the count is needed. So if only the count is needed, that means we can focus on this part to be very specific. We can focus a lot on this part. So am I clear till this point that we need to focus on the count? How is the output coming up? And why the brute force approach won't pass? Just give me a quick yes or no. Yep, in online judges, in most of the online judges, in 1 second we can only perform 10 to the power 8 operation. Okay, okay, Rishi, thanks a lot. So let's move forward. Okay, so we need to count the count of numbers that are needed. We need to now focus on this. So now if we focus on this, building up the number is a little bit easy. How? I would say you that. See, suppose we have the length of the number. Length is suppose 5, and the given value is a and b. Okay, a and b. So once I can use no A's and all are B itself. And then in the next iteration, I can just say I would use only one A. And this A would go from this point, this point, this point, this point. Okay. This A would only go from this. Like it would also be B, A, B, B, B. Okay. Okay. Like this A would go from this point to this point. Now again, it can be 2A and 3B. Then it can be 3A and 2B. Then it can be 4A and 1B. And then it can be all A. Okay. So this looks like we don't really need to build up these numbers. We just need to count. So see, so suppose the sum of this would be b multiplied by 5. Sum of this would be b multiplied by 4 plus a. The organization of a doesn't affect us, even if a is before that, even if a is after that. Why? Because the addition is an associative. A plus b is equals to b plus a. Okay, it doesn't differentiate. So if it is a plus b plus b plus b, the sum of the digits, and this is also, so both would be equal. So I can say that the arrangement would be such: if the given length is equals to 5, okay, if the given length is equals to 5, and we can only have a and b, so I can say that in the first one I would have 5b, then I would have 4b and 1a, then I would have 4b and 1a, then I would have like 4b and 1a, then I would have 3b and 2a, then I would have 2b and 3a, then I would have 1b and 4a, then I would have 5a. And these are the all the sum that I can achieve, not more than that. Okay. These are all the sum, like this are the good integers. These are good integers sum. Yep. So these are all good integers. So these are all good integers. Now these good integers would produce the best integers. Okay. So this is how we can narrow down this. Now after best integer, like after we have given that yes, this is good enough. So now these are all the values. Okay. All from all these values, if the sum contains like if the sum of digits, like from all of this, if the sum contains C or D, if the sum contains the value C or D, then we would do permutation combination. Then we would do combination, like we can just now the arrangement of the digits makes a difference. Now 1 2 and 2 1 is different. Okay, then we would just do combination using 4b 4a 1a combination and add. This is what we need to do. Okay, now till this part this should be clear. Like we are processing, we are doing the combination, and then we are returning. So let's first do till this part, because this part doesn't involve all the prerequisite that I have mentioned. Okay, this part only requires. So now let's just implement this. Mhm. Let me unshare. For our case, we need permutation because the arrangement matters, right? No, the arrangement does not matter because we need only the sum. Okay, let's make everyone slower case. Now let us just have this. So let us say that at this point, us let's just use this because this would be needed a lot. Okay. Now we would say long answer is equals to 0. Okay. The very first condition is when A is equals to B. When A is equals to B, that means we can have only one digit. So I would say when A is equals to B, so we would have 5, 5, 5, 5, 5. So we can't rearrange it. So if we have only 5, so only 5 can be only this because it can only contain this. So only one digit is there. So I would say if A is equals to B, then long sum is equals to the length of the digit multiplied by either A or B. Anyone is fine. Then after that, we would just iterate over the sum. While sum is greater than 0, we would take out the digit. So in digit is equals to sum modulo 10. Okay. And if digit is equal to C or digit is equal to D, okay, so I can't use this. I would use DJ. Digit is equal to D, then only I would return yes, a value exists. And after this point, I would just do sum divide by equal to 10. Okay. At the end, if I'm not able to return till this point, I would return 0. Now what I'm doing, so let's say we have 3 to 3. 3 to 3. So 3 to 3 modulo 10 would give me 3. That is the last value. So 1 to 3. Let's have 1 to 3. After that, this is giving me the last value. Then we are dividing it by 10. So now we have 12. Now 12 modulo 10 would give me 2. Then again we are dividing by 10, that is 1. 1 modulo 10 would again give me 1. Then again 1 divided by 10 is equals to 0. That is why we are iterating till greater than 0. This is how we are extracting the digits from the number at each point. Okay, this was the dry run of this one. Now the next condition which I was talking about, and this makes all the difference in this. So am I clear with this one? Seven to get the same sum. For this we need permutation. No, we need combination, binomial coefficient. Okay. At this point, okay, at this point, we would start the iteration. For int I is equals to 0, I is less than equal to n, and I plus plus. Okay, what I'm trying to do. So here I told you that length is equals to 5. So first I used 0a, then 1a, then 2a, then 3a, then 4a, and then 5a. So we are moving forward from 0 till the value of 5. That is why 0 till the value of n. Okay, whatever given is the length. So now I would say sum is equals to I multiplied by a plus the remaining number of values n minus I multiplied by b. See, I a to the power 0, a multiplied by 0 plus b multiplied by 5. Okay, this is what we are doing at this point. Now we would first say that we would declare a boolean and we would say OK is equals to false. Initially, we have not found C or D in its sum. So now we would iterate over this sum. Same way, we would do the same iteration. Here, instead of returning 1, we would say OK is equals to 1. Now at this point, OK is equals to 1, and we need to break, we can break from this or we don't break it. That won't make much difference. Okay. So after this, if OK is true, Then we would say answer plus equals to NCR of n comma I. Okay, NCR of n comma I. Okay, and then we would simply return the answer. We have not done NCR up till now. So first tell me if this thing is clear or not. Just this algorithm. And then we would return the answer. Quickly see this and tell me if this thing is clear or not. N is not defined. N is defined. NCR is not defined. We would write it. This is just the basic code. Now the main thing would come into picture. I told you, na, Fermat's little theorem and all other things. Is this the shortcut to find NCR? No, this is not a shortcut. I have still not wrote the solution. This is not the solution. This is just the main function. We would write the NCR function. Don't worry. We should take the sum of all the digits and then check if it is equal to C or D. No. If the sum of the digits contains either C or D as a digit, it contains as a digit or not. Okay. So now we would write the NCR function. So now stop sharing, present the screen, entire screen. So now suppose we want the value of NCR. So the value of NCR is n factorial divided by r factorial, and then we multiply it with n minus r factorial. You can confirm this by NCR formula: n factorial divided by n minus r factorial and r factorial. Okay, fair enough. So now we need the factorial. So factorials can be very large. Okay, factorial can be very large. And what we need to do is, as we know that the answer can be very, very large. So what we need to do is n factorial divided by r factorial, n minus r factorial. And we need to print this modulo 10 to the power 9 plus 7. Let's say modulo m is given. Modulo here m is equals to 1e9 plus 7. Or let's just write it 10 to the power 9 plus 7. Okay, let's say. So modulo can't be directly applied here. So the formula would be n factorial modulo m. So let me just write it like this. Yep, n factorial multiplied by r factorial modulo m. Okay, r factorial inverse multiplied by n minus r factorial inverse modulo m. So now modulo m needs to be there at each point. Modulo m r inverse modulo m n minus r inverse modulo m. Okay, and then whole modulo m is the answer. Okay, n factorial multiplied by r factorial inverse, then n minus r factorial inverse. Okay, so finding out the factorial. So 5 factorial, 6 factorial can be found out by pre-processing. How pre-processing? So we can say 1, 2, 3, 4, 5, 6. So we can say the value of 1 is 1. So the next would be the previous value plus the current value. 1 multiplied by 2 is equals to 2. 2 multiplied by 3 is equals to 6 multiplied by 4 is equals to 24 multiplied by 5 is equals to 120. 120 multiplied by 6, 120 multiplied by 6 is equals to 720. These are the values of 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial, 6 factorial. This is how you can pre-process the factorials. Okay, so the problem of factorial is now gone. Okay, we can find out factorial. But what is the small inverse thing? What is this inverse thing? So, Fermat's little theorem states that suppose we want to find A inverse modulo M. Okay, from where I am telling this, let me just show you that also. I'm just referring to this one. Yep, I'm using this formula. Okay, I'm using just this formula that n factorial can also be written as n minus 1 factorial multiplied by n. Okay, and the same idea is used in prefix sum also. So if you already know prefix sum, this won't be of much hindrance. But the problem is A inverse, to find the value of an inverse. So Fermat's little theorem states that if this mod value is a prime number, is the value of 10 to the power 9 plus 7 a prime? Yes, 10 to the power 9 plus 7 is a prime. So if A inverse modulo a prime number is given, then the value of this would be A to the power A to the power M minus 2. This would be the value of and modulo M. This would be the value of this, which is just this. I'm just telling you this. A to the power M minus 2. So as you already know that the value of M here is 10 to the power 9 plus 7. So M minus 2 would be A to the power 10 to the power 9 plus 5. So A needs to be powered up to a very large value. This is 10 to the power 9 plus 5. So we can't do this in the normal way. Like suppose we have here something like 5 to the power 8. So we just multiply 5 8 times. We can't do that. So to do the power thing in a very efficient and a fast method, we use something known as binary exponentiation. Okay. Now what is binary exponentiation? Binary exponentiation is this one. Okay. Binary exponentiation tells us that if 5 is to be multiplied 8 times, what I can do is 5 to the power 8 can also be represented as 5 multiplied by 5 to the power 4. This is one operation. And the next operation would be 5 multiplied, that is 5 multiplied 25 multiplied by 25 to the power 2. This was the second operation. And then 25 multiplied by 25, that is 625. So 625 multiplied by 625 to the power 1. So now we have found out the values in just 3 steps instead of 8 steps. So basically, the number of set bit would be the number of steps required. So instead of a linear value, we are just able to do log n. Okay. So 8 means 0 to the power 3. Okay. 0, 1, 2, 3. Number of set bit is 1, 2, 3. That is. So not set bit, the power of 2. Okay. And this would be the value required. Okay. So you can learn more about this, how we are doing this by this. So I would just be copying this. Okay, I would just write the same thing here. So am I clear till this point? Okay. So basically, you go out and you can learn a lot in this question. So now I would say const int n is equals to 1e5 plus 5. So now we would be operating on global variables so that we don't need to pass everything again and again. So now we would work on global variables because we have two functions. One is binary exponentiation, one is NCR. Okay. So 1e9 plus 7. Okay. So first let us code up this bin pow thing. Okay. So we would say that bin pow would return me a long. And we would say long bin pow. Bin pow is equals to, it would accept the parameter a to the power b modulo m. Okay. Modulo m. Now we would say if b is, so I would just copy this. This is just this. Okay. I would say if b is equals to 0, we would return 1. And then we would say long t is equals to bin pow of a comma b divided by 2 comma p. And then we would say if b modulo 2, then we would return something like a multiplied by t modulo p, and then we get out and multiply it the value of t, and then whole modulo multiplied by, and then we would else return, or we don't require this, return the value of t multiplied by t modulo p. This was just the implementation of this, nothing else. Okay. Now for each value we would also require the inverse. Okay, we would also require the inverse of each value. So first we would find the factorial of each values in one array, and we would also find the inverse factorial of that value. Okay. So now we would say void init. Okay. And we would say factorial of this value. So do we have factorial array? No. We have long factorial array of size n comma inverse factorial of size n. Okay. Like this is fn and this is if. Inverse factorial and factorial. Okay, we can't use that. So factorial ft and ift. Let's use this because this is not a reserved keyword. So now we would say factorial of 0 is equals to 1, and then we would start the iteration for long I is equals to 1 and I is less than the value n and I plus plus, and then we would say ft of I is equals to I multiplied by factorial of n is equals to n multiplied by n minus 1 factorial. So we would say ft of I minus 1. Okay. This would be nothing but ft of I minus 1, and this would be whole modulo modulo m. Okay. Seems correct. Now what would be the inverse factorial of this? So ift, inverse factorial of I, would be that value multiplied with that value a factorial is the, like, the value would be, so what is that, a to the power m minus 2. So a inverse would be. So that would be this value to the power m minus 2. So that would be bin pow. Okay. This factorial. Okay. That would be this factorial multiplied by this factorial multiplied by m minus 2 and with the modulo as expected. Okay. Now this is done. We have found out the factorial and we have found out IFTP factorial. Okay, let's just compress this factorial in a different way. Let's just do it explicitly in a different array. Okay. So now first let's go from the back. IFT of n minus 1 is equals to bin pow of ft of n minus 1 to the power m minus 2. Okay, to the and modulo m. So a factorial is equals to that value to the power m minus 2. That is why we are doing that. We are just doing explicitly from the last. Now we would start from for long I is equals to n minus 2. Okay, I is greater than equal to I is greater than equal to the value 0 and I minus minus. Okay, and here we would write the same thing. I and IFT of I is equals to I plus 1, and this should be under the bracket I plus 1 multiplied by IFT of I plus 1. Okay, modulo the value m. Okay, we are again building like only this value is enough to have the bin power for the rest of the values. Okay, now we would write NCR value. Okay, long NCR, which would have long n, comma long r, comma long p, and this would return me the value of factorial value of n factorial, see, n factorial multiplied by r inverse factorial multiplied by IFT of n minus r factorial. Okay, multiplied by IFT of r factorial, and this whole thing is modulo the value p. This is what you need to do. Okay, and this is done. The same thing. See, n factorial multiplied by r inverse factorial n minus. So the whole thing was just to do this. Okay. Now I just need to pass n comma I comma the value of m. Yep, nothing else. So let me just see how many are. So I would be making a lot of errors. Yep. 1e5 plus 5, then long bin pow, b is equals to 0, return 1, t is equals to a divided by b, then b is equals to a multiplied by 2. This is okay. Long t of inverse factorial and long f of 0. Then we are starting from f of 1, I is less than n. Factorial of I is equals to I multiplied by I minus 1 modulo m. Okay, fine. Then we are building up the from the back. I of n bin power of factorial of n minus 1 comma m minus 2 comma m. Then we are building up the factorial from the back. N minus 2, I is greater than 0, and then I minus minus. and IFT of I, then I plus is equals to inverse factorial. So we have not called the factorial thing, but let's just quickly check. Long nrp is equals to ft. So is this bracket closing, getting closed perfectly? This is one bracket, this is a second bracket. Okay, so we need to close this bracket at this point. N minus r modulo p, n minus r modulo p, and then this. Yep. So any compilation errors up till this point? Let me just see. Okay, no compilation errors. Now we would call this up. So we want to run only once. Okay, so if we want to run only once, we would initialize a bull f is equals to 0. So we want to run the any pre-computation only once. So if f is equals to 0, then only I would call f is equals to 1, and then only I would call init. And init would do everything. No? Let me just see. Init would do everything. Yep. Now let me just compile and run. Yep. Okay, seems like we are not able to just answer plus at each step we need to do modulo again. Answer plus answer modulo is equals to m. Now let's again hit this. At each step, like somewhere we are missing modulo somewhere. Anywhere? Yep, it is done. The only place I was missing the modulo was at that point. This was a long code. So now tell me if things are clear to you or not. So I would be waiting for the last 30 seconds. Okay, so that was it from my side. If you were able to solve this problem by seeing my solution, if you got something to learn, feel free to like and comment the video so that the reach of this video could be increased and this work could be justified. That's it for today. This is me, Siddharth Hazra, signing off. Thank you, everyone.